Hello students, welcome to Truneek Informatics. This is Jayanti Sharma, your physics teacher. Today we are going to discuss the chapter wave optics. Okay, so let's go. Contents introduction part, in which we will briefly discuss the wave nature of light, who proposed, how they have proposed this theory. Okay, we'll discuss that. Then we'll come to the topic wavefront and Huygens principle. Okay. So here, yes, earlier there was a lot of argument between the particle nature and the wave nature of light. Few scientists supports that light has a particle nature, whereas few supports that light has a wave nature. Okay, so both of them have the experimental proof for particle nature as well as for wave nature. So what conclusion they made, that we'll discuss later. Firstly, we go through the theories they gave for the support of particle and wave nature. Yes, Sir Isaac Newton. We all know him. He is a great scientist. So now, Sir Isaac Newton said that light is a collection of particles. He was in the support of particle nature of light. So he said light is a collection of particles, small particles moving with a great velocity. Okay, so now when they are moving in with a high velocity, so he said that these small particles, he named them as a corpuscular. Okay, this theory later known as corpuscular theory. So he said that light has a particle nature and these are moving in a straight line. He said that light is moving in a straight line and no external forces acting upon it. No other forces can affect this path of light. It will always move in a straight line. So all his theory he wrote in a book named Optics. Earlier there was no online system, so everybody gonna write their theories in a book, and he wrote a book. He wrote this theory in a book named Optics. Okay, so now when light is moving in a straight path, so he was able to prove all the concepts of light, reflection, refraction, how shadow forms, everything he was able to prove with his theory. Like if object is in the path of light, okay, so light will reflect back and the shadow will form. Okay, this was the thing. So now reflection thing, he relate this theory with the elastic collision theory. When a particle collide with the wall and reflect back, the angle of incident is equals to angle of reflection, and he relate the reflection thing with this. Okay, so at which the particle come and collide, that angle will be equal to the angle which the particle strike back. So this was there, say in the reflection theory, that angle of incident is equal to angle of reflection. And in case of rare friction, what was there, the light come, when the light come from rare medium to the denser medium, it gets attracted towards the normal. Newton said that light is getting attracted towards the normal, but why it is getting attracted towards the normal, he was unable to explain this concept. But just because Newton was a world-class famous scientist, so people used to believe it. Okay, so people accepted this theory because for many things he explained the concept and people used to believe him. So this theory was accepted by the people. And later Sir Christian Huygens, he came and he said that light has a wave nature. He said that light is a wave nature and light travels in a form of wave. But people put the question that Newton sir said, and he proved his theory on the basis that light travels in a straight line, whereas wave is a zigzag motion. Right, wave is a zigzag motion. So how could you say that light travels in a straight line? So what Huygens said, Huygens said that light has a very small wavelength. Right, light has a very small wavelength, and that small wavelength is in nanometer size. When nanometer size, it act as a straight line. It seems to be a straight line, whereas it is in a waveform. But when the wavelength is in nanometers, so it appears to be a straight line. Okay, and this wavelength is smaller than the dimension of a slit through which light passes out that slit. Okay, so its wavelength is much smaller than a slit, so it appears as a straight line. But later Thomas Young, he was the scientist who proves that the wave nature of the light experimentally. That experiment is known as Young's double slit experiment. In this experiment, he took two sources of light. Okay, he took two sources of light, and these, from when the light is emitting from these sources, it was making this pattern on the screen. Okay, this pattern contains a minima and maxima. These brighter parts are the maximas, okay, and these darker parts are the minimas. So now how these minimas are forming? When light is overlapping light, like light plus light is forming the minimas, the dark spots. Okay, and this pattern you can see, this is responsible for the light, which proves that light has a wave nature. Okay, if we consider the Newton's thing that light has a particle nature, then what should be there? The brighter spot should be at the center, okay, and the dark spot should be at the corners. That should be there, but what we actually get, we get that dark and the bright pattern on the screen. Okay, so this disapproves the Newton's theory, and they were come with the theory that light has a wave nature. Okay, so now people questioned him, if light has a wave nature, okay, light has a wave nature, then how light is able to move in a vacuum? Okay, then Sir James Clerk Maxwell, he came with the theory, electromagnetic theory of light. But he said that wave is form of electric and magnetic waves. The light wave is form of electric and magnetic waves which are perpendicular to each other and propagate in a same direction. Like this is an electric field, wave is moving like this, and this will be your magnetic field perpendicular to it. So this will be moving like this. Okay, the wave, one wave is going like this and other will be front and back, you can imagine, and in the diagram it has shown properly. So now these waves are moving perpendicular to each other but propagating in a same direction with the same velocity, and that to the velocity of light. They are propagating with the velocity of light. Okay, both. So now he was able to explain like how light travels through a vacuum. So later Sir Albert Einstein, he came with the theory that no, light is made up of photons. He was also in the favor of that light has a particle nature. So again there was a confusion. He said he proved his theory with the photoelectric effect. You all have studied the photoelectric effect. What is that? The light is bombarded on a metal surface. So the photons come and eject out the electrons from the metal surface, right? This was a theoretically given this experiment, but practically this experiment was performed by Halbach and Lenard. So when photons are coming, okay, and electrons are ejecting out, so these, he said that light is made up of photons. So light has a particle nature. But later on, Sir Einstein observed all the concepts and he come to the conclusion that no, light don't have particle nature, light don't have wave nature, light has a dual nature. Light has both the natures, particle nature as well as wave nature. So he said light has a dual nature, but which nature will dominate? It depends on the surroundings. Like if the slit has the dimension of lambda, approximately to lambda, that is the wavelength of the light. If slit has that dimensions, no, then light's wave nature will dominate, else the particle nature will be there. Okay, so light has a dual nature depending upon the interaction with the surrounding. If the dimension of the slit is approximately the size of lambda, then the light behaves as a wave nature. Okay, so in the during this course, in the ray optics, we will consider the particle nature of the light. But here in the wave optics, no, we'll consider the wave nature of the light. Okay, so wave, what is wave? What is electromagnetic wave? What is a wavefront? What is Huygens principle? All we're gonna study today. Okay, so let's start. What is wave? Wave is just a propagating disturbance. Okay, when one particle is oscillating, okay, this oscillation will disturb the next particle to it. Okay, and it's the second particle oscillation will disturb the third one disturb the fourth, and thus the disturbance will go on. Okay, so this propagation of the disturbance is called wave. Okay, so this is what how wave is forming. So now you can see this is a single particle. It's not moving, it's just oscillating at its own place, right? You can see it's just oscillating and thus forming a wave, because it's causing a disturbance to the another particles. Okay, its oscillation will cause the disturbance to the other particles, and this will go on and the wave will form. All right, so now you can say this wave is a function of space and time. This is moving in an x direction in time t. Okay, so what is wave actually is? Wave is an oscillating disturbance of some physical quantity, that is a particle, in the space and the periodic in time. Okay, so basically wave is a function of space and time. Okay, so now what is electromagnetic wave? As I told you earlier also, electromagnetic wave is nothing, just form of electric wave and a magnetic wave, and they both are perpendicular to each other, propagating in the same direction, okay, with the speed of light. Okay, now electromagnetic waves, they are transverse in nature. Okay, they are transverse in nature, and the highest point is known as crest and the lower one is known as trough, and both the waves attain their maxima and minimum at the same time. So when the wave is at their maxima, when the electric wave is at its maxima, the magnetic wave will also be at its maxima. Okay, this is what electromagnetic wave is. So now wavefront. What is wavefront? Okay, just try to understand this very carefully. So now points in a same phase. Okay, there are suppose 5-6 points in the same phase. Okay, having the same amplitude and all. So same phase, so these are oscillating. Okay, these are oscillating, and when we join these particles, okay, so the wavefront will form, like locus of the particles basically, which are in the same phase. All the particles which are in the same phase, the locus of that particles is known as wavefront. Like you can see here. Okay, so this circle thing, no, every particle, they are in the same phase. Okay, so they are oscillating with the same frequency and they are in the same phase. So now the locus of these same phase particles is forming a wavefront, and that is also known as wavefront. Okay, that is the same thing. Now wave propagate in direction perpendicular to wavefront. This is this wavefront, these are the wavefronts. Okay, so now ray, light, it is propagating, light wave is propagating perpendicular to this. Okay, these wavefronts, light is propagating, wave is propagating perpendicular to this, right? This is a circular wavefront I have shown to you in the first video. Now in the second one, you can see it is a planar phase, plane wavefront. Okay, how this plane wavefront formed? Actually, when the source is at infinity, no, when the source is at infinity, so the waves coming from that source, they generate a planar wavefront. Okay, for the planar wavefront, source will be at infinity. Okay, so now there are different wavefronts. Like if your source is linear, now what will, every single point of this will generate a wavefront, right? Every single point will generate the wavefront, and when you join these wavefronts, a cylindrical shape will form. So a linear source will generate a cylindrical wavefront. Okay, and a point source in 3D will generate the spherical wavefront. Okay, and in 2D it will generate a circular wavefront. For example, if I throw a stone in the pond, so what you can see, the waves will generate. Okay, as I throw stone in the pond, suddenly around that stone the waves will generate. Okay, what's actually happening, you in this picture you can see a particle is there. A particle is not moving, it's just oscillating at its place. Okay, and it's causing disturbance to the next particles, but it's not moving, it's at its point, it's just oscillating. Okay, so these circular wavefronts will form. And planar, as I told you, when the source is at infinity, the planar wavefront will be formed. Okay, so these are the wavefronts. Just mind that the distance between these wavefronts, the distance is d, and it will be same between all the wavefronts. The distance between one and the second wavefront will be same, and this will be equal to the wavelength of the light, approximately equal to the wavelength of the light. Okay, so now these are the wavefronts. And now let's come to Huygens principle. What is Huygens principle? So basically it is of 3 points. Like you need to learn 3 points to know what Huygens principle is. First, as I told you, like each point in a wavefront vibrate in the same phase. Okay, how wavefront formed, and from how wavefront formed, let's come to what is wavefront. Wavefront where each point of wavefront is vibrating in a same phase, right? Now all the points of the wavefront, just read out the second point, that all the points of the wavefront of light in a vacuum or transparent medium, whatever the medium is, okay, may be regarded as new source of wavelet that expand in every direction at the rate depending on their velocity. Now let me explain this. What is this? So now what they are saying, like initially there was one source from which the wave has been generated. Okay, from where the disturbance has been generated. Now this wavefront, this source will generate a wavefront. When a source, just a second, now just there is a source, this is causing, these are the nearby particles. Okay, it is causing disturbance to all these particles, and these particles formed a wavefront, right? This wavefront has been formed. Now what happened? There are many particles on this wavefront, right? There are many particles. I'm drawing it on a larger view, but there are many small particles, you all know this. Okay, and now every single particle will oscillate and disturb the nearby particle. So this will generate its own wavefront. This will generate its own wavefront. This will, similarly, all the particles will generate their own wavefronts. Okay, and if it is of planar wavefront, if the source has produced the planar wavefront, then these wavefront which this second particles, the particles on the first wavefront are producing, will be planar only. So planar source will produce the planar wavefronts. Okay, so now this was the primary one. Just understand it carefully. This was the primary one. Now this, which are producing the next level wavefronts, these are the secondary one. Okay, so these are the source for the secondary wavefront. Now when these will join these disturbances, the second wavefront will be this. So to this second wavefront, these particles, these secondary particles were the source. So these secondary particles are known as secondary source. Okay, now again, this is how wave is propagating. Okay, now the particles on this will again generate their wavefront, and this wavefront will generate the third one. So now this will be the secondary one. Okay, so primary was the same, the primary source was the one, but next to generate other wavefronts, so points on the first wavefront will act as a secondary source to generate the second wavefront. Again, similarly, it will propagate on the outer side. Outwardly it's moving, outwardly. Okay, now let's come back. So you can see in the picture there is a original wavefront. This one. Now now particles on original wavefront, they are producing a further wavefronts, point on wavefront. Okay, and this is a new wavefront. So the points on the wavefront, they produce the second wavefront. So these are known as secondary source. Okay, also this was the example of plane wavefront. Now in the second picture you can see there is a source. Okay, source has produced the first wavefront. This is the first wavefront. Now on this first wavefront, these are the sources which are producing their wavefronts. This you can see. These are the wavefronts produced by the particles on the first wavefront. So these particles can be known as the secondary source. These are the secondary source to produce this second wavefront. Okay. So now these are the secondary source to produce the second wavefront. Similarly, now further these will generate their wavefronts and move, and so that this wave is propagating outward. Okay, so this was the Huygens principle. One thing more, that velocity of the wavefront, the velocity by which these wavefronts are propagating outward, this will be equal to the velocity of wave. That's why a wave is forming, no? So velocity of wave will be equal to the velocity of wavefront. This is what Huygens principle said. So now this is a very important question according to the syllabus. Now whenever this question has come, so you need to write these 3 points and you need to draw these figures to explain what Huygens principle actually says. Okay, so basically the Huygens principle says that there is a secondary source from the primary disturbance. A secondary source is generated, and this secondary source will generate the secondary wavefront. Okay, primary wavefront, and points on the primary wavefront will generate the secondary wavefront, and the points will be known as secondary source. So this is what Huygens said. So next we'll discuss how reflection and refraction will be there based on Huygens principle in our next class. So that is all for today's class. Thank you very much. So see you in the next class. Bye bye. Thank you.